What is our place in the Milky Way and our place in the universe? In ancient times, many people had the idea our planet Earth to be at the center of the universe, as stated by Aristotle and Tomuse in their Ptolemaic Aristotelic concept of the universe. According to this model, Earth is at the center of the universe, and all the other celestial bodies orbit around it. Today, lots of people think the same, but is this really the case? To answer this question, let's try to travel in the universe through space and time. We will start our travel from our planet to reach, in the end, the extreme boundaries of the universe. During the 1600s, Galileo Galile, the famous Italian astronomer, was one of the first people during modern age to have some doubts about the geocentric model of the universe. Thanks to telescopic observations, he was able to demonstrate our Earth is not at the rotation center of planets and the Sun, but really it is the Sun itself. Moreover, observing planet Jupiter, he discovered that the giant planet is the rotation center for its moons. So Galileo became aware that the center of the solar system was the Sun, not the Earth. The solar system is made by a star, the Sun, 8 planets, and different types of minor celestial bodies like comets, asteroids, and dwarf planets. Well, the Earth isn't at the center of the solar system. Maybe is the closest planet to our Sun. No, it isn't, because it is only the 3rd planet from the Sun. The closest planet to our star is Mercury, followed by Venus, and then Earth. The Earth moves around the Sun, our star, just like all the other celestial bodies in the solar system do. This implies that the Sun, and not our planet, is the center of rotation of the solar system. The Earth takes a year, 365 days to travel its orbit, and its average distance from the Sun is 150 million kilometers, which is the measure unit of distances in the solar system known as the astronomical unit, and abbreviated AU. Why do we talk about average distance? Because the orbit traveled by the Earth around the Sun is not circular but elliptical, and this means that there will be an aphelion, i.e. the point of the Earth's orbit farthest from the Sun, just over 1 AU away from it, and a perihelion, the point of Earth's orbit closest to the Sun, just under 1 AU. An alternative way to define the astronomical unit passes through the light time. In particular, we can say the average distance Earth-Sun is equal to about 8 light minutes. This means that sunlight takes 8 minutes to arrive on Earth, so that the sunlight we see at a certain moment is not that of that moment, but it is the sunlight which left from the Sun 8 minutes earlier. In other words, if the Sun went out, for example, at 2:30 p.m., we would only notice it at 2:38 p.m. Or again, if you could travel aboard the Star Wars Millennium Falcon, it would take you only 8 minutes to travel from the Sun to the Earth, when in reality it takes a few years. To give a more concrete idea of the dimensions of the solar system, if the Sun were a sphere with a diameter of 14 centimeters, Pluto would be at 700 meters from the Sun, like 7 regular soccer fields. The nearest celestial body to Earth is the Moon, our satellite. To reach it, you should take 3 days off. It's the same time taken by Apollo astronauts to cover the distance of nearly 400,000 kilometers that separate the Moon and Earth. But if you had Star Trek's Enterprise and travel at maximum curvature, you would only take less than 2 seconds to reach the Moon. Now let's begin to move towards the outer solar system. At a distance of 2 to 3 AU from the Sun, between the orbits of Mars and Jupiter, we would meet the asteroids' main belt. Asteroids are those small rocky bodies whose dimensions span from a few kilometers to a few hundred kilometers. They are so small that they aren't visible through unaided eye, but only through telescopes. We could reach asteroids in a few years with a traditional spaceship or probe. Let's move on. We would need around 10 years and 40 AU to fly by Pluto, one of the outermost bodies of the solar system. Try to imagine it in your mind. If you were on Pluto's surface and had to look at our planet, you would only see a pale blue dot. That is the same sight captured in 1990 by Voyager 1 NASA probe, while it was leaving Neptune behind. Around Earth, only the dark vastness of the universe, barely illuminated by starlight. Now we have left behind our solar system, and we are going to enter the interstellar space. To get to Proxima Centauri, the closest star to Earth, we have to cover a bit more than 4 light years. We remember a light year is the distance covered by light in a year in the vacuum and is equal to about 10,000 billion kilometers. Distances begin to become big, since the Millennium Falcon would take more than 4 years, traveling at light speed to reach Proxima Centauri. And the Sun? Okay, it's at the center of the solar system, but it is also at the center of the Milky Way. If you continue to travel on board your beautiful spaceship, you will discover it. But it is a very, very long trip, so you will need much patience. The Milky Way is our galaxy. It is an immense group of stars held together by the force of gravity. It has the shape of a flattened disk with a bright core in the center, where the star density is very high, and spiral arms around it. Around the core, there is a spheroidal halo, which extends outside the galactic planet. At this point, it could be useful to introduce the parsec, equivalent to 3.26 light years, to measure the dimensions of our galaxy. So our Milky Way has a diameter of around 30,000 parsec, which are equivalent to 100,000 light years. So if we were back on the Millennium Falcon again and had to cross the Milky Way from one side to the other, traveling at the speed of light, the fastest thing there is, it would still take us 100,000 years to cross it all. Or to put it another way, if you were to send a WhatsApp message to your friends on the other side of the galaxy to decide what to do on the weekend, your message would take about 100,000 years to arrive. Assuming that your friends respond immediately to the message, the response would take another 100,000 years to get back to you. Keeping the same analogy seen before, with the Sun represented as a 14-centimeter diameter sphere, our Milky Way would have a dimension of 100 million kilometers. That is equivalent to make 2,497 turns of the Earth along the equator. The galactic halo has a diameter of the order of 30 kiloparsec and is populated by old stars that are stars with an age double that of the Sun. In the spiral arms, instead, there are younger stars, like the Sun, located within the arm of Orion, a secondary arm of the Milky Way between the arms of Perseus and Sagittarius. Our star, the Sun, is only one of the estimated 200 billion stars in the galaxy. Galaxy with capital initial letter because it is the galaxy par excellence. Our galaxy, in fact, its name derives from the Greek galaxius, the way of milk, referring to an ancient Greek myth for which the Milky Way would represent nothing other than the milk sprinkled out of the breast of the goddess Mira while nursing little Hercules. If it happened to you to find yourself on a mountainside during a clear summer night, looking up at the sky, you will certainly have noticed that whitish milky band that crosses the whole sky. It is the Milky Way. Since the Sun is inside one of the spiral arms of the Milky Way, from the Earth we see the galaxy as a streak precisely because we are looking at the galactic plane edge on and from inside it. It's like to try to observe all of our condominium from our flat. We will only see just our neighbor's flat, not the entire condominium because we are in it. But is the Sun at the center of the galaxy? No. Its distance from the galactic center is about 8,000 parsec, or if you prefer, 26,000 light years. Our star takes around 250 million years to go along its orbit around the galactic center. This means that since its formation, it's only made around 25 orbits around the center of our Milky Way, traveling at 215 kilometers per second. And it is good that the Sun is not in the center of the galaxy, because in it there is a supermassive black hole, Sagittarius A Star, a monster with a mass equal to about 4.3 million times the solar mass and an immense gravitational field such that even light is not able to escape. This huge black hole is located in the direction of the constellation of Sagittarius, a constellation observable in the summer for the inhabitants of the northern hemisphere and in the winter for those in the southern hemisphere. Since a black hole does not emit light in the visible band, the same we see with our eyes, it is not visible directly through a telescope, but can be detected through indirect methods. Number 1, radiation emitted by the accretion disk around the black hole. A black hole is surrounded by an accretion disk made of matter that orbits spiraling around it. This matter sooner or later falls into the black hole. Before ending up in it, however, it is heated to very high temperatures of the order of 1,000,000 degrees, producing electromagnetic waves of very high energy, such as X-rays and gamma rays. Number 2, study of the orbits of the stars closest to the black hole, studying the movement of the stars in the area of the galactic center, it was noted that they seemed to rotate around nothing, because apparently there was no visible celestial body in that area. Studies conducted by research groups led by astrophysicist Andrea Ghez and Reinhard Genzel, who won the 2020 Nobel Prize in Physics together with Roger Penrose, over the course of many years, have shown the existence of a celestial compact body at the center of our galaxy, right in the area where the black hole Sagittarius A Star is located. And what about the Milky Way? Is it at the center of the universe? Even in this case, the answer is negative. The Milky Way belongs to the local group of galaxies, with a dimension of 10 million light-years or 3.1 MPC megaparsec. We remember that 1 MPC is equal to 1 million PC, and that 1 PC equals to 3.26 light-years. The local group includes more than 70 galaxies, most of them of small size. The center of mass of the local group is between the Milky Way and the Andromeda Galaxy, M31, and the local group, together with the Eridanus cluster, Fornax cluster, and Virgo clusters of galaxies, belong to the local supercluster with a diameter of around 100 million light-years. It is thought that our universe contains around 200 billion galaxies, along with 200 billion stars. Can you imagine that with satellites, space probes, and telescopes we have explored so far, only a very little percentage of the universe? In conclusion, our Earth is not at the center of the galaxy, neither of the universe, but only a small planet around a small star which orbits in a peripheral zone of a spiral galaxy similar to many others. Citing Carl Sagan, is only a mote of dust suspended in a sunbeam. How many galaxies orbit around the Milky Way? In the solar system, the planets orbit the sun, and in the galaxy, the stars orbit around the galactic center, which is usually a supermassive black hole. But did you know that galaxies also orbit around other galaxies? Yes. These are the satellite galaxies, a type of small galaxies which orbit the largest ones like the Milky Way. As you heard, it turns out that the Milky Way is so large that other galaxies orbit around it just as planets orbit the sun. Would you like to know what these satellite galaxies are and what effects they produce in our galaxy? Let's find out. Our galaxy is a fantastic place. In addition to being the galaxy we live in, it is also a towering object that stands out from other nearby galaxies. Although the Milky Way is not the biggest galaxy in the universe, it is a vast galaxy within the local group. The local group is a collection of at least 54 galaxies within a region about 10 million light-years across, including the Milky Way, the Andromeda Galaxy, and several smaller galaxies. In general, the satellite galaxies of the local group have fewer stars. They are much fainter than the Milky Way and other giant galaxies, making them more challenging to detect and study. The satellite galaxies of the Milky Way are fascinating because they are the closest celestial objects to us after stars and planets. Astronomers have identified at least 50 satellite galaxies in the region around the Milky Way. However, some are so faint that the most advanced technology has only recently detected them. Some of the most essential satellite galaxies orbiting the Milky Way are Large Magellanic Cloud. The Large Magellanic Cloud is an irregular dwarf galaxy that orbits the Milky Way at a distance of approximately 163,000 light-years. It is one of the satellite galaxies of the Milky Way and is visible to the naked eye from the southern hemisphere. It was named after the Portuguese explorer Ferdinand Magellan, who observed it during his voyage around the world in 1519. The Large Magellanic Cloud is also one of the most popular objects among the amateur astronomy community. It is very bright, despite only containing around 10 billion stars, making it a galaxy smaller than the Milky Way, which contains about 100 billion stars. Despite its relatively small size, the Large Magellanic Cloud is known for its intense star formation activity. The star formation rate in this galaxy is estimated to be about 0.1 to 1 solar mass per year, which means that new stars are being formed at a very high rate, practically one new solar system every year. In addition to its star formation activity, the Large Magellanic Cloud is known for its many globular clusters. Globular clusters are ancient spherical clusters of stars believed to have formed simultaneously with the galaxy that hosts them. Throughout history, around 60 globular clusters have been identified in the Large Magellanic Cloud, making it one of the galaxies with the most known globular clusters. It was also an object of study with great historical importance because it was used to measure the Hubble constant, a measure of the universe's expansion rate. Variable stars known as Cepheids have been used to measure the distance between Earth and the Large Magellanic Cloud, and thus calculate the Hubble constant. This has led to important discoveries in cosmology and allowed astronomers to understand better the universe in which we live. Small Magellanic Cloud. It is another satellite galaxy of the Milky Way, located at a distance of approximately 200,000 light-years. Like the Large Magellanic Cloud, it is visible to the naked eye from the southern hemisphere and is also named after Ferdinand Magellan. It is an irregular dwarf galaxy with about 7 billion stars, making it smaller than the Large Magellanic Cloud. However, like its big sister, it is known for its intense star formation activity and is estimated to have a star formation rate of around 0.02 to 0.03 solar masses per year. The Small Magellanic Cloud also hosts globular clusters, although in fewer numbers. Around 15 globular clusters have been identified, but it is believed that there may be more that have not yet been observed. In addition to its importance in measuring the Hubble constant, the Small Magellanic Cloud has also been studied for its role in forming low-mass stars and its relationship to supernovae. Supernovae are the result of the explosion of massive stars, and the Small Magellanic Cloud has experienced several observed supernovae throughout history, which is very impressive considering that these star explosions can significantly impact the intergalactic medium and may influence the formation of new stars in the galaxy. Canis Major Dwarf Galaxy. This is a satellite galaxy of the Milky Way, located 25,000 light-years away. It is a spherical dwarf galaxy with an estimated mass of 500,000 solar masses and an old metal-poor stellar population. Metal-poor refers to the low abundance of elements heavier than helium in a star or galaxy. Metallicity is an essential parameter in astronomy because it relates to age and stellar evolution. Metal-poor stars and galaxies tend to be older than metal-rich stars and galaxies because they formed early in the universe when the production of elements heavier than helium was far less than today. It has also been detected that this galaxy does not have young stars, but that most are very old. The lack of bright young stars suggests that the star formation stopped long ago. That is why studying this type of galaxy is essential to understand the universe's evolution. The Sagittarius Dwarf Galaxy. It is located about 81,000 light-years away. It is a spherical dwarf galaxy discovered in 1994 and is one of the closest galaxies to the Milky Way. Despite its relatively small size, the Sagittarius Dwarf Galaxy has been the subject of intense study due to its possible role in the formation and evolution of the Milky Way. Studies indicate that our galaxy is tearing apart the Sagittarius Dwarf Galaxy, tearing its stars out and incorporating them into our own. This has led to the hypothesis that the dwarf galaxy could be the source of the stream of stars found in the galactic halo of the Milky Way. Impressive, don't you think? The Fornax Dwarf Galaxy. It is located in the constellation of Fornax, approximately 460,000 light-years from us. It's a spherical dwarf galaxy discovered in 1938. The Fornax Dwarf Galaxy has been the subject of intense study because of its large population of globular clusters and dense groups of stars that orbit the galaxy. Furthermore, it has been used as a reference to study the structure and dynamics of dwarf galaxies in general. Despite its scientific importance, the Fornax Dwarf Galaxy has a curious history. It was discovered by Australian astronomer Harlow Shapley while working in South Africa in the 1930s. Shapley named the galaxy after the constellation Fornax, representing a smelting furnace. He was fascinated by the idea that the galaxy might have formed from material ejected by a supernova explosion in a red giant star, similar to how metals are melted in a furnace. Sculptor's Dwarf Galaxy. It's located at a distance of approximately 280,000 light-years from us. It's a dwarf spheroidal galaxy discovered by Harlow Shapley in 1937. Like other nearby dwarf galaxies, the Sculptor dwarf galaxy is one of the most studied by astronomers due to its proximity and richness in globular clusters. It is one of the dwarf galaxies with the most globular clusters known. Although it is a relatively small galaxy, the Sculptor dwarf galaxy is also notable for its density of dark matter, making it one of the best candidates for studying the distribution and properties of this matter. Consider that dark matter is, to date, one of the greatest mysteries in the universe. An interesting curiosity about this galaxy is that it is the brightest dwarf galaxy in the night sky at radio waves, making it an essential object for studying cosmic background radiation at these wavelengths. The Leo 1 dwarf galaxy. The Leo 1 dwarf galaxy is a satellite galaxy of the Milky Way located in the constellation Leo at a distance of approximately 820,000 light-years from us. It's one of the brightest and most massive dwarf galaxies known. Despite its small size, the Leo 1 dwarf galaxy is interesting to astronomers because of its high heavy element, metal, content compared to other dwarf galaxies. This makes it a metal-rich galaxy instead of the metal-poor galaxies mentioned above. Another interesting fact is that the Leo 1 dwarf galaxy is approaching the Milky Way at a very high speed, making it one of the few known objects in the universe that moves through space at such a high speed. The Leo Dwarf Galaxy 2. The Leo 2 dwarf galaxy is another satellite galaxy of the Milky Way, located in the constellation Leo at approximately 700,000 light-years from us. Despite its small size, it is an interesting galaxy to astronomers as it has a very pronounced elliptical shape, distinguishing it from many other dwarf galaxies. Leo 2 has a low content of heavy elements, metals, which makes it a metal-poor galaxy, similar to other dwarf galaxies in the local group. Although Leo 2 has few globular clusters compared to other dwarf galaxies, it has a significant population of variable stars that astronomers use to determine the distance to the galaxy. In addition, the Leo 2 dwarf galaxy has been home to one of the brightest supernovae observed from Earth, the supernova SN 1991bg, which was discovered in October of 1991. This supernova was essential to astronomers because it helped refine their understanding of the physics of supernovae and their role in forming heavier elements. The study of satellite galaxies is an exciting field of research that leads us to explore the deepest corners of our universe. Through these small galaxies orbiting the Milky Way, we learn more about the nature of dark matter, galaxy formation, stellar evolution, and many other fundamental areas of astronomy. In addition, satellite galaxies witness the most extreme events in the universe, such as supernova explosions and supermassive black holes, allowing us to understand better how the cosmos works on a large scale. Despite their modest size, these galaxies offer a wealth of information and mysteries astronomers are working hard to unravel. By studying these galaxies, we are also reminded of the importance of looking beyond the obvious and looking for what lurks in the shadows. Just as satellite galaxies are hidden from the naked eye behind the Milky Way, many things in life can go unnoticed if we don't pay attention.
Someone once said to me that if the Milky Way was New York, the stars we are able to see with our naked eye would be the equivalent of a courtyard. Our galaxy hosts billions and billions of stars, and it is counted that for spiral galaxies, the equivalent of 3 solar star masses are born per year. Today we want to take a look at the most interesting stars in the Milky Way. Number 1. Tabby Star, KIC 8462852. Officially named KIC 8462852, the star is 1,200 light-years away in the constellation Cygnus and is about 1.4 times the mass of the Sun. What intrigued astronomers about this star is that a transiting object caused it to dip in light by as much as 20%. Now, usually planets are responsible for some dips in the light when they pass in front of the star, but 20% was too much. That object had to be something far, far bigger than a planet. Someone proposed weird explanations to that dip in light. Explanations included a swarm of comets or, as a last resort, aliens. The idea was that something causing that deep transit might be an artificial structure, including a theorized Dyson swarm of objects harnessing power from the star. Of course, this was not the case. There is no alien civilization in front of Tabby Star. In fact, subsequent observations have likely ruled out anything artificial. Scientists think that a debris field of dust is responsible for the large dip in luminosity, though there are various arguments as to the nature of the dust. Anyway, the intriguing fact here is that the astronomers haven't witnessed anything like the original detection since, though a series of observations recently detected 5% dips in light, which is much lesser than 20%, but still far too large to be a planet. Number 2. Mira. Mira is not a single star. It's actually a star system, a binary system with a large pulsating red giant. Mira A is the red giant and Mira B is a much smaller white dwarf. They are companions. To the naked eye, Mira A is a variable star that essentially disappears and then reappears almost every 11 months. What makes Mira so interesting? What's going on in the system is that Mira A, the red giant, is shedding material into space, and some of this material then accretes around Mira B. This spreading of mass leads to the accretion of two interesting phenomena in the system. First, the system itself is shedding material into the interstellar medium. This gives to Mira the superficial appearance of a giant comet, though the trailing material stretches for light years. That is much greater than that of a comet's tail. The second phenomenon is that there seems to be a protoplanetary disk formed around Mira B from the ejected material from the red giant. This is strange because protoplanetary disks are typically found around young stars rather than dead white dwarfs. This could mean that new planets are forming around a dead star, something not known to happen before it was discovered in the system. We just have to see what the next studies will suggest. Number 3. SAO 206462. We've just seen that Mira resembles a comet. What if I told you that there is a star that looks superficially like a spiral galaxy? In fact, it is a trait of SAO 206462. This is a very young star surrounded by a protoplanetary disk, which is not unusual for young stars still forming planets. But what's unusual here is really the structure of the disk. It is arranged in a spiral arms shape. This star is relatively close to us, and its protoplanetary disk itself is huge, about twice the size of the orbit of Pluto. Scientists think that the spiral structure seems to be due to recently formed planets within the disk, being arranged in such a way as to shepherd and shape the disk into spiral arms through gravity. In this system, planets are still forming. It's a newborn star system. Once the planet will be formed, the spiral structure, and indeed the visible disk, will probably disappear. Number 4. BPM 37093. No, it's not referred to a song's tempo. BPM 37093, located in the constellation of Centaurus, BPM 37093 is about 50 light-years from Earth. This star was originally thought to be a white dwarf, but it was later found to be incredibly dense. It has a little bit more mass than our Sun, but it's way denser, with all the mass compacted down to about a third of the size of the Earth, making it effectively a crystallized star. White dwarfs in general are believed to be composed of carbon and oxygen, and a prediction from the 1960s said that cooling white dwarfs should begin to crystallize. If we found a pulsating variable white dwarf star, we could test our predictions. BPM 37093 is interesting because it allowed us to do just that. So we tested our crystallization concept, and guess what? It turned out to be correct. In the case of BPM 37093, it was found to be as much as 90% crystallized, though estimates of this vary. So when you start subjecting carbon to high pressure and it begins to crystallize, you get diamonds or something like it. It could be said that this white dwarf, or at least at some depth, essentially turns into a big, big, big diamond. Would you still call it a star? Number 5. MY Camelopardalis. A study of the binary system MY Camelopardalis shows that the most massive stars are made up of the merging of smaller stars, as predicted by theoretical models, smaller to bigger. Most of the stars in the Milky Way formed in binary or multiple systems. MY Camelopardalis, MyCam, consists of two of the most massive objects known. In fact, its components, two stars of spectral type O, that is blue, very hot and bright, with masses respectively equal to 38 and 32 times the mass of the Sun, are still in the main sequence and are very close. Their orbital period lasts less than 1.2 days and represents the shortest so far measured in this class of binary systems. This suggests that the two components virtually originated as they are today. The two stars were almost in contact when they formed. The fate of the binary system will be the fusion, that is, the merging of the two components before the two stars have time to follow their own evolution, which will lead to the formation of a single object with a mass greater than 60 solar masses. These results demonstrate the validity of some theoretical models according to which more massive stars are formed from the merging of less massive stars. Number 6. Vega. We live with the concept that the poles of a planet are usually colder than the equator. Can we say the same thing about stars? Well, telescopic observations in 2006 revealed that Vega is whipping around so quickly that its poles are several thousand degrees warmer than its equator. The star, which rotates every 12.5 hours, is at 90% of its critical rotation speed, or the velocity at which the object would tear itself apart. Another interesting thing about Vega is that astronomers discovered an asteroid belt surrounding it, suggesting the chance for planets within the midst. The layout suggests that there are two areas, an outer region with icy asteroids and a region closer to the star where warmer space rocks reside. Vega is by far one of the most known stars of our Milky Way because astronomers use it as a reference star for luminosity measures. Number 7. HD 101065. Within the Centaurus constellation is hiding a southern sky constellation just beyond what our eyes can see, and it is a truly weird star. It's called HD 101065. It is about 4 times the mass of the Sun, and what makes it so special is that HD 101065 star is cooking up the kinds of elements we don't normally see in stars, including uranium. The Sun, like many stars, doesn't typically fuse anything heavier than nickel, which is number 28 on the periodic table. Jason Wright, an astrophysicist, called the star his favorite astrophysical enigma in a blog post. In fact, most of these elements have short half-lives, so something may be replenishing them. Searches for a small pulsar have failed, but it could be that the star cooked up super heavy elements that are decaying into ones never found on Earth. Number 8. HD 140283. The interesting fact about HD 140283 is its age. The universe is 13.8 billion years old. HD 140283, by all appearances, is 14.4 billion years old. That is a problem with cosmology. The age estimate is based on its composition, brightness, and distance. The star is 190 light-years away. Well, it has to be said that the minimum estimated age is 13.2 billion years, and the margin of error of the 14.4 billion year estimate probably places it comfortably but barely within the age of the universe. But we need more observations in order to increase our precision. Anyway, if it's not as old as the universe, it was born right after the Big Bang. The study of this star could lead us to a better understanding of the first moments in the life of our universe. Number 9. CP 1919. In 1967, a radio signal was detected by Jocelyn Bell and Anthony Hewish. The signal had a 1.3 second period and 0.04 second pulse width. It originated at celestial coordinates 19 hours 19 minutes right ascension plus 21 degrees declination. Due to its almost perfect regularity, it was at first assumed to be spurious noise, but this hypothesis was promptly discarded. The discoverers jokingly named it Little Green Men 1, LGM-1, considering that it may have originated from an extraterrestrial civilization, but Bell soon ruled out extraterrestrial life as a source after discovering a similar signal from another part of the sky. The original signal turned out to be radio emissions from the pulsar CP 1919 and was the first one recognized as such. Before the nature of the signal was determined, the researchers considered the possibility of extraterrestrial life. We did not really believe that we had picked up signals from another civilization, but obviously the idea had crossed our minds, and we had no proof that it was an entirely natural radio emission. It is an interesting problem. If one thinks one may have detected life elsewhere in the universe, how does one announce the results responsibly? Who does one tell first? This pulsar became famous in the pop culture
as the English post-punk band Joy Division used an image of CP1919's radio pulses for the cover art on their 1979 debut album, Unknown Pleasures. Have you seen that cover? Number 10. The Sun. This is the star everybody knows. Why is it important? Well, simply because the Sun is the only star we know that hosts life so far. The Sun is the star at the center of the solar system. It is by far the most important source of energy for life here on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles. The Sun is a G-type main sequence star, G2V, based on its spectral class. The enormous effect of the Sun on Earth has been recognized since prehistoric times. The Sun has been regarded by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of solar calendars, one of which is the Gregorian calendar, the predominant calendar in use today. We are glad to live in its neighborhood. If the universe is teeming with aliens, where are they all? It is said that the Italian physicist Enrico Fermi asked himself this question in the context of a conversation on the evaluation of the probability of coming into contact with intelligent extraterrestrial life forms. Apparently, you can only give an answer by working your imagination and setting out to make excellent science fiction. But in the course of the video, we will see that this question is not so far-fetched. There was someone who tried to give a quantitative answer instead, strenuously trying to stay within the context of pure scientific speculation. He did it by elaborating an equation that, once solved, would allow us to have a reliable estimate of how many other civilizations share with us this strange condominium that could be our galaxy. This someone is astronomer Frank Drake, one of the pioneers in the radio search for extraterrestrial intelligence. He devised a famous formula known as the Drake equation, which should help us estimate the number of technological civilizations potentially existing in our galaxy. The equation was presented for the first time in a conference at Green Bank in November 1961. The initiative was intended to trigger a fruitful discussion on the real prospects of a search for non-terrestrial intelligence by radio means. The formula that Drake presented aimed to highlight with a mathematical relationship the specific factors that play an important role in the birth and development of intelligent civilizations in the universe. As it will be seen, each term of the equation represents a key element in the evolution of a civilization, and the resulting numbers have a purely theoretical value. It should not be forgotten that any evaluation can be made in such a context as an exclusively probabilistic appearance, given that most of the values can be assigned to the various parameters are devoid of experimental relevance and therefore only theoretical. Although a univocal solution to this equation is not currently conceivable, it is of undoubted scientific interest, since it illustrates the potential of this type of investigation very well. Drake's hypothesis starts from the consideration that the number of advanced civilizations that may exist in our galaxy, possessing the interest and the ability to communicate over interstellar distances, can be reasonably estimated using the following equation. N is the number of intelligent civilizations presumably present in our galaxy, capable of making contact with each other. We must pay attention to the fact that here we are talking about civilization and not about life in the most general sense of the term. The reason for such a distinction made by Drake probably lies in the current technological impossibility to go and see for oneself if there are forms of life elsewhere. So the hope of discovering if, for example, a civilization exists on Vega or not is entirely placed on the possibility of receiving a phone call from there, a message organized in such a way as to tell us in an unambiguous way that life hasn't only taken its root there, but which has also reached a degree of cultural evolution such as to allow it to communicate its presence. N star represents the number of stars in our galaxy, estimated at the order of 200 billion stars, more or less similar to our Sun. That is a huge number, and this enormity is the main reason why even the hope of not being alone is among the last to die. The most optimists pose N equals N star, that is, they hypothesize that forms of intelligent life have developed around all the stars. but at the present state of our knowledge, it is an impossible position to defend on the basis of a good physical and historical political sense. In an alternative writing of Drake's equation, instead of n star, r appears, which is the average annual rate of star formation during the entire life of the Milky Way. R is obtained by dividing the number of galactic stars by the age of the galaxy. It represents the only parameter on which it is possible to hazard estimates, because it is calculated from the number of existing stars and the number of years of life of the Milky Way. Currently, its value is assumed to be 20. Fp represents the fraction of stars with a planetary system. This term is subject to continuous revisions by astronomers who, thanks to the considerable boost given by new technologies, in recent years are finding more and more unequivocal evidence of the presence of planets around many of the stars examined, thanks to missions such as the satellites Kepler, Gaia, TESS, and other similar missions. However, double stars that are at least 50% have a hard time supporting planetary systems due to celestial mechanic problems and reciprocal perturbations. But we can also be optimistic because then other factors will rule out double or multiple systems. Fp could be assumed equal to 0.5, i.e. half of the stars have a planetary system. Ne represents the part of the fraction of these planets that have conditions similar to ours. The subscript E stands for Earth, therefore potentially suitable for the development of life, a distance from their star that can provide a quantity of heat and light neither scarce nor too intense, i.e. that places it in what is usually referred to as habitable zone, in an area of the planetary system where the tidal effects of the other planets are negligible. A planet in which there is the presence of the essential elements for the birth of life, and with such gravity as to be able to retain an atmosphere that is able to induce a greenhouse effect so as to protect the soil from harmful ultraviolet radiation. The estimation of Ne is more complicated, and it will be Kepler, TESS, Gaia, and the other similar space missions to help us. So far, we have discovered a prevalence of giant, often gaseous planets very close to the central stars. Several rocky planets have also been discovered, but with greater difficulty than the first due to their smaller size. Ne then depends a lot on the type of star. The small and cold ones have a very narrow and close habitable zone, and therefore the useful planets should huddle close to them. But in this case, the tidal force would block them like the moon with the Earth, and they would be destined to always show the same face to the central star with obvious dramatic consequences. Giant stars give more space but live much less, and so on. Each star has its own problems of urbanization. A decent estimate for this parameter could be 1, i.e. one habitable planet for each star with planetary system. Fv is the fraction of suitable planets in which life actually develops and evolves towards very complex forms. This variable takes into account how many of these life-forming planets were actually able to do so. Life as, and perhaps more than any other event within our universe, is a complex phenomenon, subject to too many variables, and the physical, chemical, and biological path that leads to its development can be diverted or interrupted by a whole series of factors, some currently known and many others unknown. Among the former, we cannot but think, for example, of the fall to the ground of one or more asteroids the size of the one that here on Earth is supposed to have abruptly interrupted the existence of dinosaurs. A fairly sensible estimate could lead to a value of 0.2, i.e. one planet out of 5 would allow life to evolve. Fi represents the fraction of these planets on which intelligent life forms develop. This term must take into account how many, among all those lucky planets that have developed life, have been able to guard it and allow it to evolve as intelligent life. What actually makes life evolve up to intelligence? It certainly takes time, fairly constant climactic conditions, few external disasters, falling asteroids, exploding supernovae, etc. Fc is the fraction of planets where intelligent life forms develop interest in interstellar communications. His estimate is also quite complicated. A very dense belt of asteroids that would prohibit space travel or orbital telescopes, either a much denser cloud cover or even cosmic modesty, intolerance towards others, agoraphobia, or simply a civil evolutionary stage but not technologically adequate for interstellar communication could all be elements that make the value of this fraction increase or decrease. D is the average duration in years of a technologically advanced civilization. It tells us that civilizations are born, grow, reach a cultural apogee and economic prosperity. But it also says that sooner or later they suffer the catastrophe of often self-destructive decline. If an alien civilization were willing to communicate with other civilizations scattered throughout the cosmos, but in its evolutionary hysteria, the nightmare of a total war was opposed to destroy the entire race or to leave a few survivors unable for various reasons to resume a discourse oriented towards cosmic communication, we would never know of its existence. It should be noted that the most delicate aspect of the calculation consists precisely in the evident difficulty of assigning reasonably approximate values to the parameters, as there is no experimental evidence that allows a sufficiently precise assessment of their value to be made. Everyone can advance personal hypotheses and practice calculating the value of n by inserting more or less reliable data on the basis of the results deriving from the most recent discoveries in astronomy and exobiology. One can be fundamentally pessimistic or optimistic. The remarkable fact is that, in many cases, the estimate leads to a probability of the existence of intelligent life within our galaxy very close to 1. In recent years, following important astronomical discoveries, it has been gradually possible to assign more and more precise values to some variables. However, at least 3 of the parameters of the Drake equation remain entirely theoretical. According to some scholars, however, it is possible to give a fairly precise estimate of the value of the individual terms of the Drake equation, an assessment that seems to lead some to the conclusion that life exists elsewhere, convincing many others instead of its absence. The beauty of this equation is ultimately its most obvious flaw, that its apparently rigorous scientificity attracts many serious scholars who are able to make extremely varied and often strongly conflicting numerical evaluations on the possible value of its result. The orbital data and the mass of exoplanets discovered so far are constantly increasing, and this data is closely linked to the availability of new and more sophisticated instrumental technologies, which in the near future would allow us to directly reveal the existence of terrestrial-type planets. However, the scientific community is quite in agreement in considering the common existence of terrestrial-type planets orbiting around solar-class stars, spectral class G2V of the Hertzsprung-Russell diagram. With similar arguments, it is reasonable to hypothesize that the stars of the main sequence of a spectral class approximately similar to the Sun have a similar distribution of planets, with orbits stable enough to allow the existence of liquid water indispensable for the origin and development of life. Drake's equation tells us that we will find civilization only where conditions are the same or slightly different from those we find here on Earth. The claim to scientificity of this equation and the theory that supports it could then seem to waver if one looked at it as a multiplication of unknowns, but one would make the mistake of not considering the great correctness of the method adopted to conduct the search for the value of its single terms. It is precisely to protect this correctness of the scientific method that it has been chosen to restrict the field of action of this research to what we know for certain about life and its requests from our direct experience as living beings. This is about a piece of very recent history that is honestly pretty cool. On August 8, 2021, the star RS Ophiuchus burst into view in Earth's sky as what astronomers call a nova. The reason this is so special, as noted in the intro, is that this nova that was born was one that you could actually see from Earth without the help of various devices. So you wouldn't have needed a telescope or a satellite to go and witness this. If you were on the right spot on Earth, you could just go and see it. In a dark sky, you can see it shining in the Constellation Ophiuchus, the Serpent Bearer. If you don't know what that is, we recommend you look it up so that you can try and see this nova. Just as important, though, was that this wasn't a blink and you'll miss it moment. Rather, this is something to where the star is honestly increasing in its brightness over time, which means that it's actually gaining strength and power the longer it's in this form. RS Ophiuchus normally shines at around a magnitude of 12. It's usually much too dim to see with the eye or even most backyard telescopes. But when it went nova, the explosion caused the brightness of the star to increase in a way that honestly no one saw coming, which is why this is such a special thing, or at least special in certain ways given what we know about it. Because trust us when we say that RS Ophiuchus is much more than meets the eye. We say that because RS Ophiuchus is one star in a very special system. that system being a recurrent nova system. What does that mean? Put simply, it means that this is a system of stars that has novas happen somewhat regularly. RS Ophiuchus is part of a two-star system. One is a white dwarf, a highly compact evolved star. The other is a red giant. This is very important for multiple reasons, not the least of which is that due to the proximity of these two stars, the white dwarf star is constantly going and pulling in stuff from the red giant, which isn't a bad thing per se, but when it pulls in too much from that red giant, boom, a thermonuclear explosion happens and a nova is the result, much like we had here early on in August. Now, as for the frequency of the explosions for this particular star, it honestly depends. The two stars orbit one another, and thus this is really a cycle of things going on over time. In the case of RS Ophiuchus, it also exploded back in 2006, and there have been other nova explosions recorded going back over 125 years. So yeah, these things really do go and happen a lot. Which brings us back to the system itself, because while there are plenty of systems out there in the galaxy and universe that have nova explosions happen, they're not meant to happen frequently or at regular intervals. RS Ophiuchus and its system is truly rare in that you can almost time how long it'll take before a new nova explosion happens. So thus, by the clock we can now go on, that would mean that the white dwarf will likely explode again in 2036. A while away for sure, but many people will get to see the nova happen then, much like we got to do now. Getting back to things, you might be wanting to go and see this nova star for yourself now, but as we alluded to earlier, you might not exactly know where it is, so we're here to help you with that. The Constellation Ophiuchus is currently in the south after sunset. It lies above the better-known constellation Sagittarius and its familiar teapot asterism, which is closer to the horizon. If you look above the spout of the teapot and cross the cloudy swath of the Milky Way, you'll come to the region of sky where RS Ophiuchus lies. The brightest star in Ophiuchus is Rizalhag, located near the top of the constellation, and the second brightest is Sabak, located near the bottom. RS Ophiuchus lies about midway between the two stars, but farther to the left, the east. And if for some reason you aren't able to find it, there are plenty of people who were able to take pictures of it from when they were observing it in the sky. Here are the tweets from a few happy stargazers who happened to catch a glimpse of it. Reports overnight of a new explosion of my favorite nova, RS Ophiuchus, detected optically and in gamma rays. Last outburst was 2006, the one before in 1985, and the subject of my PhD. The eruption of the recurrent nova RS Ophiuchus making its grand appearance in our AS/AS/SN images following its outburst 2 nights ago. Yesterday, the variable star RS Ophiuchus in the constellation Ophiuchus exploded. Although it is 5,000 light-years away, the blast is bright enough to see with the unaided eye after sunset. So as you can see, there were a lot of people paying attention to this very special explosion because it's not something that happens every day. And it's fair to say that those who were able to see it and study it are very happy, because who knows when something like this will be able to happen again. Let's go back to the process behind the nova for a bit, because there's still a bit to talk about in terms of the hows and whys and such. For example, if it explodes, how can it explode again? A good question, and one that speaks to the nature of the white dwarf star itself. You see, stars have limits in terms of what they can handle in terms of heat, pressure, and of course mass. The nova is caused, as talked about before, when it absorbs so much mass from its neighboring red giant star that it has to explode. But when it explodes, what it's doing isn't detonating itself into oblivion like you're thinking about in terms of a regular explosion, but rather it's an explosion of mass that it's expelling all the built-up mass that it has within it. Think of it like a geyser. Geysers of water are one that go and release the pressure it's under by expelling it and the water that is contained within. Old Faithful, as it's known, is honestly on a cycle because of how much pressure is built up within a specific amount of time, and it's the same thing with this star here. It'll go and explode out all the excess mass it has and thus become brighter in the process until it finally dies down. And to be clear, one of the reasons we can't see this expulsion of mass is because it's being sent out of the star at about 2,600 kilometers per second. That's a really fast-moving set of mass. The Fermi Gamma Ray Telescope also detected a gamma ray source at the time and location of the nova, confirming that an outburst was indeed taking place. Further proof that people have been watching the system for a while and couldn't help but notice what was going on. Now, there's a catch to this explosion, if you will. While it's been able to do this kind of pressure release over time, there's a limit to what it can hold in the overall. This is known as the Chandrasekhar limit, and if that limit should be surpassed, the star will explode in a critical mass kind of way and not go nova, but go supernova. And for those who know what that means, you understand why it's a big deal. For those who don't know, it means that the star won't just go and expulse its built-up mass. It'll actually explode with the power of the star that'll wipe out everything in its path. And then it won't have to worry about its cycle anymore because the red giant star will be quite gone. These are the most powerful stars ever witnessed, from a distance at least, by man, and many are wondering just when it'll happen for this star. At present, it doesn't seem to be something to worry about, but obviously that could change over time. And when that happens, the recurring nova system will indeed change, even if we don't know how much it'll change at present. Supernovas as a whole are something that scientists try and study when they can for the simple reason that they don't happen that often, which is saying something when you're talking about the known and unknown that we're constantly watching and studying. Granted, most astronomers agree that supernovas sometimes happen in the hundreds per year, but that doesn't mean we get to see them. And they have to be in certain galaxies like the Milky Way. But by studying them, we can go and examine things like distance in space, which is not as easy to measure as some would state, and the effects they have on their surroundings. The other part here is that when a supernova happens, the building blocks of new stars, as well as a slew of other elements, are put into space by the dying stars and the other entities around it. Scientists like to observe this to see just what space as a whole gets after these key moments. So should this happen to RS Ophiuchus, not only will we be able to see it due to where it stands in our sky, we'll be able to research it quite heavily. But again, we honestly don't know when it'll go supernova or if it'll go supernova at all. So thus, we wait. Speaking of RS Ophiuchus, one of the things that can't be ignored here is that there are potentially new things to learn about this nova now than was able to be done in 2006. After all, that's 15 years of technology, probes, satellites, and more that have gone up and have been getting better in their photo capturing, data collecting, and more. It's entirely possible that as scientists try and observe the star for as long as it's visible, that they'll be able to get new data that'll help us understand the star, its system, and more. Is that a guarantee? No, of course not. Few things in space are guaranteed. That's just how it works. But it's the potential for discovery that honestly keeps people going even when it doesn't seem like there's nothing to be discovered. Enjoy the sight of the Milky Way while it lasts. Can you spot your city in this fantastic picture? Chances are you might be living in a very light-polluted area. For over 3 billion years, life on Earth has evolved in harmony with the natural cycles of light and darkness. The sun, moon, and stars have provided the sole sources of illumination, shaping the natural day-night pattern that has guided countless species. However, our modern cities have now become beacons of artificial light that overpower the darkness, disrupting this delicate balance and forever altering our environment. The consequences of this profound shift may initially seem intangible, but a mounting body of evidence demonstrates the tangible and wide-ranging negative impacts of our brightened night sky. Firstly, the health of human beings is at stake. Not only that, the ecosystem and wildlife are also suffering as a result of our illuminated cities. Additionally, our relentless illumination of the night sky poses a grave threat to stargazing and astronomical research. The Milky Way, a breathtaking spectacle that has inspired awe and wonder for millennia, may soon vanish from our skies if we fail to take action. Light pollution obscures our view of the cosmos, hindering not only our ability to appreciate the vastness of the universe, but also our scientific understanding of it. Darkest versus most polluted regions. The composite picture displayed at the beginning of this video was created using data collected by the Suomi National Polar Orbiting Partnership satellite. The satellite gathered this information over 9 days in April 2012 and 13 days in October of 2012. It required a total of 312 orbits and 2.5 terabytes of data to obtain a clear and comprehensive view of every portion of the Earth's land surface and islands. The image reveals that regions such as China, America, Japan, Europe, and Egypt, as well as the area between Qatar and Kuwait, emit the most intense brightness. Moscow was identified as the most light-polluted city in 2018, closely followed by Riyadh in Saudi Arabia and Montreal in Canada. Furthermore, it is evident that certain parts of the world have significantly lower levels of light pollution. These include regions in Australia, New Zealand, Africa, and South America. Nonetheless, it is important to consider that the satellite image only represents one perspective. It offers a view from space down onto the Earth's surface. However, there are substantial differences when observing from the ground towards the vastness of space. This raises the question of how the presence of light pollution impacts our surroundings. Although the picture provides insight into the extent of pollution, it fails to depict the effects on the ground level. These can lead to bad consequences. Montreal versus Aoraki Mackenzie Reserve. If you're not able to spot a single star in this picture, don't worry, it's not because you're blind. This picture of Montreal at night shows how light pollution can have a strong impact on the surroundings. Pictures like this serve as a stark reminder of the impact of light pollution on our surroundings. As humans continue to invent and innovate, most environmental pollution on Earth can be attributed to our own creations. From the automobile emissions contributing to climate change to the harmful plastics littering our oceans, our inventions have had far-reaching consequences. Among these inventions is the electric light bulb, often hailed as one of the greatest human achievements. While it has undoubtedly improved our lives by guiding us home and creating a cozy atmosphere, it has also brought about an unintended consequence: light pollution. The excessive artificial lighting in urban areas obscures our view of the night sky, making it difficult, if not impossible, to appreciate the beauty of the cosmos. Fortunately, there are still dark places in the world where the night sky remains untouched by light pollution. One such place is the Aoraki Mackenzie Dark Sky Reserve in New Zealand, the largest reserve of its kind in the Southern Hemisphere. Spanning the Aoraki Mount Cook National Park in the Mackenzie Basin, this reserve has been established to preserve the pristine dark skies that are free from light pollution. From this remote location, one could witness the breathtaking beauty of the Milky Way like never before. Moreover, being in the Southern Hemisphere allows for the observation of the Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. Imagine being able to see two extragalactic objects at once with your own eyes, without the need for telescopes. Crazy, right? Some people say that if you have never seen the Milky Way from places like this, you've never really lived. In any case, how different is the sky in Montreal compared to the Aoraki Reserve? Is it possible to quantify the disparity? The answer is a resounding yes. Various measurements and scientific techniques can be employed to assess the levels of light pollution in different areas, allowing for a quantitative understanding of the contrast between the two skies. The most used method is based on the Bortle Scale. The Bortle Scale. The Bortle Dark Sky Scale is a numerical scale used to measure the brightness of the night sky and stars at a specific location. It assesses the visibility of celestial objects and the impact of light pollution and sky glow. Created by Johnny Bortle, it was published in 2001 to assist amateur astronomers in comparing the darkness of different observing sites. The scale ranges from Class 1, representing the darkest skies on Earth, to Class 9, which indicates inner-city skies. High ratings on the Bortle scale signify areas with significant light pollution, making them the worst for stargazing. A Class 9 city, for example, will have a brightly lit sky where constellations are barely visible, except for a few objects like the Moon, planets, and bright star clusters. Forget about the Milky Way. You won't even be able to dream of it. These conditions are common in the brightest cities worldwide. A Class 5 rating means that the Milky Way is faint or invisible near the horizon and appears washed out directly overhead. Light sources can be seen in most or all directions, and clouds will appear brighter than the sky. As you move down the scale from 5 to 1, the viewing experience becomes more impressive. For instance, the Aoraki Reserve is associated with a Class 2 rating on the Bortle Scale. Here, the Andromeda Galaxy is easily visible to the naked eye, along with the Magellanic Clouds. The Milky Way appears stunning, and the Moon can even cast shadows during twilight. This offers a truly magnificent sight for observers. According to physicist Christopher Kaiba of the German Center for Geosciences, the phenomena of light pollution is rapidly causing the night sky to brighten, with an alarming annual increase of approximately 10%. This concerning trend poses a dire threat, as it could potentially wipe out the visibility of all but the brightest stars within a generation. For instance, a child currently born in an area where 250 stars can be observed at night would only have a diminished view of around 100 stars by the time they reach 18 years old. If these projections prove accurate, it is distressing to contemplate that the captivating sight of the Milky Way may become invisible to our eyes as soon as 2050. So enjoy its sight while it lasts. Effects on birds' migration patterns. Of course, in ancient times, humans used to light up their nights with fire. When we discovered electricity, things rapidly changed, and a lot of good things came with it. However, like carbon dioxide emissions and plastic, too much of a good thing has started to negatively impact the environment. Light pollution, the excessive or inappropriate use of outdoor artificial light, is affecting human health, wildlife behavior, and our ability to observe stars and other celestial objects. To start, light pollution can have a significant impact on birds' migration patterns. Birds use natural cues, including the position of stars and the moon, to navigate during their migrations. Artificial light can disrupt these natural cues, leading to a range of problems for migrating birds. Indeed, birds are often attracted to artificial light sources, particularly those that are bright and steady. This can lead them to circle the light source, becoming disoriented and wasting precious energy. Moreover, light pollution can obscure natural landscapes, making it difficult for them to recognize landmarks they use for navigation. This can result in them becoming lost and disoriented. Ultimately, artificial light can disrupt the normal behavior of birds during migration. For instance, birds may be more likely to feed at night under the influence of artificial light, which can disrupt their natural feeding and resting patterns. This is an interesting point because something similar happens to humans. Indeed, artificial light has a huge impact on our circadian rhythms. Ever heard of them? Effects on human health. To make it simple, human beings have internal biological clocks that regulate various physiological processes such as sleep-wake cycles, hormone production, body temperature, and cognitive function. These clocks, known as circadian rhythms, are synchronized with the 24-hour day-night cycle. However, electronic screens and LED lights have been found to disrupt these rhythms by suppressing the production of melatonin, a hormone essential for regulating sleep. To counteract this, it is advisable to avoid using phones after 7 p.m. to improve sleep quality. In addition to sleep disturbances, disrupted circadian rhythms can also lead to cognitive impairments. Memory, attention, and decision-making abilities can be negatively affected when these rhythms are not properly regulated. Furthermore, studies have demonstrated that chronic exposure to light pollution and the resulting disruptions in circadian rhythms can significantly increase the risk of various health problems. These include obesity, diabetes, cardiovascular disease, and certain types of cancer. It is crucial to understand that light pollution is not merely an issue of obstructing our view of the night sky. It has profound implications for our overall well-being. The negative impact of artificial light on our health should be taken seriously. By being mindful of our exposure to electronic screens, adjusting our habits, and prioritizing healthy sleep patterns, we can minimize the adverse effects of light pollution on our circadian rhythms and mitigate the associated health risks. What can we do? So how can we make the world a darker place? The solution may be simpler than you realize. By taking small daily actions, we can minimize the negative effects of artificial light on our environment. For example, cities should consider installing motion sensor lights or timers for outdoor lighting, ensuring they are only active when necessary. They could also utilize shielded fixtures that direct light downwards, preventing it from dispersing into the sky or neighboring areas. Additionally, we should choose warmer amber-colored lights with lower color temperatures, around 2700 K, rather than cooler bluish lights. These kinds of lights are less disruptive to wildlife and are also better for stargazing. Lastly, it is important to be mindful of our indoor lighting usage. We can make a difference by turning off lights in unoccupied rooms or when natural light is sufficient. By taking these simple steps, we can contribute to creating a safer planet for everyone. So why not start today?
In 1933, Fritz Zwicky thought there was a problem related to the galaxy cluster Coma. The galaxy cluster studied by Zwicky appeared to contain some 400 times more matter than ordinary visible, i.e. luminous matter. The content of the luminous matter was estimated from the amount of light emitted by the cluster. However, there was no response to that finding. 40 years later, in the 1970s, the problem was rediscovered. Scientists found that it concerned almost all of the galaxies, even the Milky Way galaxy. Research of Vera Rubin discovered that the galaxies rotate in a way that cannot be explained by taking into account visible luminous matter. There had to exist a type of dark matter. It is an invisible substance that seems to make up almost 85% of all the mass and roughly 26% of the mass energy content of our universe. Ever since, scientists have tried to resolve the problem of the existence of dark matter through various attempts. One way to solve the problem would be finding a particle to possibly complete the Standard Model. The most important property of such a particle would be that it is not subject to the electromagnetic force. This is also why dark matter is invisible in all electromagnetic wavelengths. In order to detect such a particle, engineers and physicists are collaborating to build sensitive detectors, but still, the final conclusion has not been made. Another solution could lie in the so-called MOND theory. Modified Newtonian Dynamics, MOND, proposed by M. Milgram in 1983, is a phenomenological approach attempting to provide an explanation of the rotation of galaxies without invoking hidden matter at all. It doesn't make use of the mysterious dark matter. One point of evidence in support of dark matter is the way in which the speed of stars, gas, and dust in a galaxy varies with their distance from the center of the galaxy, known as the galactic rotation curve. Every astronomer knows what a rotation curve of a galaxy is because it is extremely important for the determination of the mass content of a galaxy. Most of a galaxy's visible matter is concentrated near the center of a galaxy, which astronomers call the bulge. So we would expect that more central stars should move much faster than stars in the outer regions. Thus, the rotation curve is expected to decrease with distance. But what scientists usually found, starting from Zwicky and Rubin, is that most galaxies have a fairly flat rotation curve, meaning outer stars move about as fast as inner stars. This is amazing, and this is still an amazing result. And how can we explain this? One way to explain this is, indeed, to introduce the presence of dark matter regions in the galaxies. This led to a theory of dark matter. Nowadays, scientists are struggling to find more evidence or confirmations in order to corroborate the dark matter theory, and a lot of them are focusing their attention on the Milky Way. Does dark matter exist in our galaxy? Well, from what we know, the Milky Way owns dark matter too. In fact, the visible disk of the Milky Way galaxy is thought to be embedded in a much larger, roughly spherical, huge halo of dark matter. The dark matter density drops off with distance from the galactic center. It is now believed that about 95% of the galaxy is composed of dark matter. a type of matter that does not seem to interact with the rest of the galaxy's matter and energy in any way except through gravity. The luminous matter makes up approximately 9 times 10 to the 10th solar masses. The dark matter halo is likely to include around 6 times 10 to the 11th to 3 times 10 to the 12th solar masses of dark matter. But we have just a vague idea. That's why scientists are making some efforts in order to understand better this phenomenon. In particular, a new paper was published by Charlie Conroy, Center for Astrophysics, Harvard and Smithsonian, and his colleagues, in which they discuss the topic starting from the study of the path story of the well-known LMC, the Large Magellanic Cloud. Let's see what they found, but first, we want to say something about the LMC. The Large Magellanic Cloud, or LMC, is a satellite galaxy of the Milky Way. At a distance of around 50 kiloparsecs, on the order of 160,000 light-years, the LMC is the second or third closest galaxy to the Milky Way after the Sagittarius Dwarf Spheroidal, about 16 kiloparsecs, and the possible dwarf irregular galaxy known as the Canis Major Overdensity. Based on readily visible stars and a mass of approximately 10 billion solar masses, the diameter of the LMC is about 14,000 light-years, 4.3 kiloparsecs. It is roughly 100th as massive as the Milky Way and is the 4th largest galaxy in the local group after the Andromeda Galaxy, M31, the Milky Way, and the Triangulum Galaxy, M33. The LMC contains a stellar bar that is geometrically off-center, suggesting that it was a barred dwarf spiral galaxy before its spiral arms were disrupted, likely by tidal interactions from the Small Magellanic Cloud, SMC, and the Milky Way's gravity. With a declination of about minus 70 degrees, the LMC is visible as a faint cloud from the southern hemisphere of the Earth and from as far north as 20 degrees north. It straddles the constellations Dorado and Mensa and has an apparent length of about 10 degrees to the naked eye, 20 times the Moon's diameter, from dark sites away from light pollution. The Milky Way and the LMC are predicted to collide in approximately 2.4 billion years. So, we just learned that a hefty galactic dwarf is falling toward the Milky Way. It is known as the Large Magellanic Cloud. What scientists found is that this dwarf galaxy is plowing through and pulling on the fog of dark matter that surrounds our galaxy. Sparse stars float like the tips of dark matter icebergs in this galactic ocean. The study's owners have definitively detected a pileup in those stars, and presumably the dark matter too, that this dwarf has left in its wake. How was the research done? Charlie Conroy, Center for Astrophysics, Harvard and Smithsonian, and his colleagues plotted the distances and positions of 1,301 giant stars in our galaxy's outermost reaches between 200,000 and 330,000 light-years from the galactic center of the Milky Way. They used Gaia satellite data from the European Space Agency that provided these stars' positions in the sky, while data from NASA's Wide Field Infrared Survey Explorer mission provided their distances. What they found is that 2 regions on the sky stand out for their thickness of halo stars, one above the galactic plane and one below. The latter extends toward the Large Magellanic Cloud in the south. The denser region of stars in the north is even larger, spanning a quarter of the sky. At first, the team made some computer simulations to see the trace of the LMC. Then they compared the observed stellar densities to computer simulations that trace the gravitational effects of the Large Magellanic Cloud as it falls in toward the Milky Way. Nicolás Garavito Camargo, University of Arizona, led the work on the simulations. He showed that the dwarf galaxy should create a wake behind it as it falls through our galaxy's halo, trailing stars and possibly dark matter behind it. Luckily, or I would say logically, the expected wake matches the dense region below the plane. This is a beautiful result, because it suggests that our simulations, and so our physics below them, well describe the reality of our universe. But the most important thing is that scientists think that wake is made up of dark matter. How can they suppose the nature of the wake if dark matter is invisible? Well, they made some cinematic studies. That is, they studied the velocity of stars that the wake drags along with it. This is how they detected it. Another important thing they could infer of the large Magellanic Cloud is that the dwarf is making its first pass around the Milky Way. In fact, if the LMC was looping around our galaxy for a second or third time, any such wake would be smeared out. The fact that we see it so clearly provides strong evidence that the dwarf is passing around the Milky Way for the first time. But of course, the Milky Way and LMC attract each other. This is why the Milky Way itself moves in response to the massive dwarf, which has a tenth of our galaxy's heft. As the center of mass shifts, a weaker but wider-ranging effect gathers stars closer together in a large region above the galactic plane, and this explains the below region they found. This is a very cool result, says Geraint Lewis, University of Sydney, who was not involved in the study. This gravitational wake behind a large dwarf galaxy was predicted a while ago, and it was expected that stars should pile up also, but given that the halo is so sparse, it has taken a lot of work to identify the signature in the stars. However, there's still a lot that we don't know about our galaxy's dark matter halo. For example, what shape does it have? Results like this will help astronomers redefine our understanding of the Milky Way and, in general, of our universe. Also, as we get more data, we start to understand that the dark matter halo is not a simple structure, and our calculation of the properties of the halo will surely be more complex. The existence of a wake of dark matter does offer some interesting possibilities in unraveling its nature. The wake's discovery, for example, points to higher density regions of dark matter where particles may annihilate more frequently, but still rarely, betraying their existence by the photons they emit. Such regions might become targets of future dark matter searches. The theorists of the group are also working to fine-tune the simulations, turning knobs to see what dark matter scenarios best match observations. What has been a purely theoretical prediction has now been validated by observational data, providing a compelling argument for the existence of dark matter, says study co-author Gurtina Besla, University of Arizona. Before concluding this video, we want to stress the fact that nowadays there's a lot of other evidence to support dark matter, but there have also been alternative models such as modified Newtonian dynamics, MOND. In this model, the radial acceleration of a star deviates very slightly from that predicted by Newtonian physics and general relativity. The difference is too small to notice on the scale of our solar system, but on a galactic scale that difference adds up, producing a galactic rotation curve just as we observe. MOND and related theories can accurately describe rotation curves, but they fail to describe other effects, such as large-scale galactic clustering and the mass distributions of colliding galaxies, so dark matter is the dominant model in astrophysics. But new research on the radial acceleration of stars could bring MOND back into favor.